During the Summer Games Done Quick 2022 speedrunning marathon, a run was shown off during the task block of The Legend of Zelda Ocarina of Time called Triforce %. It started with a real-time speedrunner, save state, performing what looks like the start of an any % run, which aims to set up some arbitrary code execution to warp to the credits as quickly as possible. However, at what would be the end of the run, things go a bit off course. Link is positioned in a very precise location, then the controller is connected to TaskBot, a hardware interface that can feed extremely precise inputs to the console via the 4 joypads. For the next several seconds, Link seems to move around erratically as TaskBot makes some mystery inputs. Then, save state takes the controller back, and suddenly a bunch of beta and unused content has been unlocked. The commentators, Soren and Dwango AC, talk about what's being shown and all, but as time goes on, more and more seemingly custom content is revealed. The run continues with Link claiming the Triforce, fulfilling many years of urban legends about Ocarina of Time's plot. And then an entirely custom scene with new graphics, audio, and recreated versions of Link and Zelda from Breath of the Wild is loaded, and messages from the marathon's live chat appear in the game, all in real time. This video will aim to explain how this was all done, including how to set up and execute the initial arbitrary code, as well as how all of the custom content was injected into the game. The Triforce % run can be broken down into 3 parts. Part 1, setting up the arbitrary code execution via a glitch called stale reference manipulation. This is what the first 9 minutes or so of the classic Ocarina of Time gameplay is about. Then when everything is prepared, Part 2, executing the initial arbitrary code payloads. This is when TaskBot takes over the first controller for about 20 seconds. As you might be able to guess, code is being injected and executed via the controllers, and this happens so quickly and precisely that a normal human being would not be able to pull this off. Then, Part 3, showing off all of the things that the injected code is capable of. In the Triforce % run, this starts off with opening a debug menu and showing off some beta content that is still in the original game's code. This evolves into some custom story elements and ends with an entirely brand new cutscene with custom models, textures, shaders, voice acting, and real-time injection of chat messages. First, let's look at Part 1 and see how Ocarina of Time can be glitched to allow for arbitrary code execution in the first place. The majority of this part is also applicable to the current any % run done on the original N64 console, only instead of simply warping to the credits scene, a payload is injected through the controllers. But what do I mean when I say injected through the controllers? The state of the buttons and analog control stick for each of the 4 controllers is stored in memory at address hex 8011D790. Each controller port takes up 6 bytes. 2 bytes for all of the buttons, A, B, Z, start, the D-pad, L and R shoulder buttons, and the C buttons. 1 byte for the analog stick's X offset, 1 byte for its Y offset, 1 byte for an error code in case the controller is unplugged, and then 1 padding byte that is always 0. Altogether, this makes 24 bytes. By pressing buttons and moving around the control stick on the controllers, the values in these memory addresses change. Under normal circumstances, the game's code can read these values to know what the player is currently pressing and update the game accordingly. However, this memory here is just like any other memory in the system. Game code is also found in memory and is executed here all of the time. What if we were to jump execution or call a function that is defined to be at the same location as this controller data? The data representing the state of the controllers can be treated as MIPS assembly instructions, and they would be executed just like any other code. The exact code that would run would depend on exactly what buttons and what angle the control sticks are currently being held. This is the goal. It may be very difficult for a real player to hold 56 buttons and 4 analog sticks to precise X and Y values in order to consistently end up with useful instructions, but some sort of robot would have no problem replicating many different button combinations at blistering speeds. Now, of course, the original game never intends to execute the controller data as code, so we have to use some glitches to do that somehow. Luckily, within the starting area of the game, we can achieve arbitrary code execution, which, as its name suggests, allows arbitrary code of our choice to be run. The key glitch which enables this is known as stale reference manipulation, or SRM for short. Before I explain how SRM works, let's look at how some regions of memory, called a heap, work in Ocarina of Time. If you've studied any amount of computer science, you're probably familiar with the heap. It contains dynamically allocated memory blocks of various sizes used by all sorts of objects and functions. In Ocarina of Time, there is a specific heap, the actor heap, that contains code and data for all of the currently loaded actors in the game. An actor being any sort of object or entity, like Link, NPCs, rupees, and even some hidden objects and triggers. There are two main kinds of things held in the actor heap: actor overlays and actors themselves. Actor overlays contain the code that is run for each type of actor, how they behave and react to other actors and gameplay elements. If there are multiple instances of a single actor, say a rupee, only one actor overlay needs to be loaded into the heap, since they all use the same code. Then there are the actors themselves, which hold the data for each individual instance of that actor, stuff like position, rotation, and the actor's state. As actors are loaded into the game, they are allocated memory on the heap. The game will search the heap for a free chunk of memory that is large enough to load the actor or the overlay into, starting from the start of the heap at address hex 801DAA00 and working down to 8023AB90. If a new type of actor is loaded, the corresponding actor overlay is loaded as well. When transitioning to a new area, all of the actors in the new area are allocated to the heap before all of the old actors are freed. This results in actors and overlays being assigned memory locations that aren't consistent. Their location in memory will depend on exactly how many actors were already loaded and how they were organized within the heap structure. So this signpost actor may be located right here in the heap now, but if you were to leave the area and come back, it might be somewhere else in the heap. Some actors may need to keep a pointer, or reference, to another actor in their data. For example, the boomerang actor keeps a reference to the actor that it has grabbed. Under normal circumstances, if an actor references a second actor, the second actor should not unload and be freed from the heap before the first actor either unreferences it or unloads. If this were to happen somehow, we would call this a stale reference. The pointer this actor has is now pointing to a memory location that is not being used anymore. What this means is that if another actor were to be allocated to the heap in the location where that old actor used to be, the first actor would then be pointing to an actor that it probably shouldn't have access to. Going off the boomerang example, by unloading the actor as grabbed by going through a room transition while it is off screen, a different actor will take its spot. This would cause the boomerang to modify that new actor's position instead, which can cause something to teleport when it should not be able to. This is an example of an actor being allocated in the same memory location as an older actor. What would happen if an actor overlay loaded into this memory location instead? Well, when the boomerang modifies an actor's position, what is it actually doing? For all actors, their X, Y, and Z coordinates in the world space are held at offsets hex 24, 28, and 2C within their allocated memory block in the heap. So the boomerang will take the address of the pointer to the actor it is holding, add these values to it, plus hex 30 for the heap node header, and write data at those memory locations. This would effectively modify the X, Y, and Z coordinates of the actor it is holding. However, if it had a stale reference that is now pointing to an actor overlay instead, some unintended side effects would occur. Each actor overlay is different, but the important thing is that these are blocks of code instead of blocks of data. The boomerang is still going to obliviously write data to offsets hex 24, 28, and 2C into this memory block. However, it will be writing 32-bit float data into places where 32-bit MIPS assembly instructions are supposed to be held. If the code for this overlay gets executed after the boomerang modifies it, it will likely crash since the code has been overwritten with data, which is likely not going to result in a valid, sensible assembly instruction. However, what if we could control exactly what values are being written by the actor and exactly which instructions from the actor overlay are being overwritten? We could effectively modify the code that the game executes, and we can make it do whatever we would like. This is the essence of SRM. In the Triforce % run, we achieve SRM by getting Link to pick up an item while it is cold, that is, not being drawn because it is either off-screen or too far away from the camera. Then, without allowing the item to be uncalled, passing through a loading zone so that the item unloads and Link has a stale reference, and then coming back through the loading zone to get a particular actor overlay to occupy the memory that was originally taken up by the item Link is holding. Before doing all that though, the heap has to be prepared. While it may seem like actors being loaded and freed from the heap is random, it is purely deterministic. By collecting items, such as rupees, we prevent them from loading back in each time this loading zone is triggered. Also, since Mido is nearby, the direction the camera is facing is important too. If the camera is facing towards the main room, Mido won't unload, causing his overlay to stay put while his actor instance moves around in memory. By switching the direction of the camera while walking back and forth over this loading zone, all of the actors and actor overlays in the heap get shuffled around in a very precise way. After this seemingly arbitrary walking back and forth in that hallway, the heap will be laid out in such a way that will allow a specific actor overlay to load in the location we want later. Normally, the camera sticks around Link as you are playing the game, making it pretty much impossible to pick up an item and walk around with it while it is cold. By using a glitch to force the camera to always stay behind Link, and then using another glitch to move around while a text box is open, we can get the camera to move far away from Link, which will cull away any actors that are near him. Because of the heap manipulation we did earlier, we know exactly where in the heap the data for this rock actor is, hex 801F7310. When Link is carrying an actor, he updates the position and rotation of that actor so it appears in his hands above his head. The rotation of an actor, a 16-bit value, is stored at an offset of hex B4 from the start of the actor's data. So if the rock is stored at this address, we know that this address will be the one that is modified. In this case, the rotation value written is just Link's rotation value, so that they are oriented in the same direction. Since it is very easy to control what angle Link is facing just by walking around, this is the value we can use to write arbitrary data, which gets interpreted as arbitrary code when executed as part of the actor overlay, as we'll see in a moment. While the camera is still stuck in position really far away, we carry the invisible rock all the way to the loading zone and walk back and forth through it one last time. The rock Link is holding gets unloaded because it is called away, and because of the heap manipulation we did earlier, an actor overlay gets allocated in the same memory region that the rock took up earlier. What is this actor overlay? It belongs to an actor known as the Wonder item, which is an invisible actor that triggers the collection of invisible items, such as rupees. There is a function within this actor overlay that gets run whenever the Wonder item is uncalled, when it is in front of the camera. This lines up with the address we have control over, thanks to the SRM. The exact instruction we end up overriding is a branch instruction. Now, each instruction is 32 bits wide, but the rotation value is just 16 bits, so we can only manipulate half of the instruction, the branch offset. It was originally just 2, but we can replace this branch offset with any value from hex 8000 to 7FFF, which is negative 32,768 to 32,767 in decimal. This means when the game executes this instruction and branches, we can get the program counter to jump over 32,000 instructions forward or backward, which is quite a large range. This instruction is located at address hex 801F73C4, so we can jump as far forward as hex 802173C4 and as far back as address 801D73C8. Unfortunately, the controller data is stored at hex 8011D790, which is outside of this range. What this means is that we have to daisy chain jump instructions. With this modified branch, we can jump execution to somewhere else in the heap, and because of our very precise heap manipulation, we know exactly where everything is loaded. This means we can encode a bigger, better jump instruction somewhere within the memory of the heap that jumps directly to the controller data, then have our modified branch instruction branch to this new jump instruction, which is exactly what we do here. The main disadvantage of the branch instruction is that we only have 16 bits to work with. The controller data is so far away, and a branch instruction won't cut it. In contrast to a branch instruction, a jump instruction dedicates 26 bits to the jump address, which will get us there in one go. Are there 32 bits somewhere else in the heap that are easy to manipulate that we can use? Near the start of the heap is the actor data for Link himself, and within that data are two 16-bit words that hold more rotation data. One is Link's movement angle, which direction he is moving, and one is Link's targeting angle, the last angle Link had while he was targeting something. All we need to do is orient Link at a very precise angle so that those two angles, when interpreted as a single MIPS instruction, encode a jump instruction that jumps execution to the controller data. It's not super easy to do, but by aligning the camera with exact cardinal directions, and then performing actions that are known to rotate Link by an exact amount, we can get the angles we need. Here are the values that get written in preparation for the arbitrary code execution. At address hex 801F73C4, the rotation value of hex 8F80 is written in order to make the branch instruction jump to hex 801DB1C8. This isn't the exact address of our bigger jump instruction, but it's close enough that the game eventually makes its way down to our instruction anyway. It is located at hex 801DB25C, and encodes a jump to address hex 8011D77C. Again, this isn't exactly the controller data, but rather right before it. All of the instructions before it are safe to execute without anything bad happening. So now everything is set up, but how do we get the code we modified to run? The code related to the wonder item will only run when the invisible item is in front of the camera, and we've made careful sure that it hasn't been up to this point. By standing in this spot, the camera will slowly pan over, and the moment the wonder item becomes uncalled, the code runs. Since the controller data is now being run as code, it is very likely that the game will just crash unless the data can be interpreted as valid MIPS assembly instructions that also allow the game to return to normal game execution. This is where our friend TaskBot comes in, and where we take a deep look into Part 2 of Triforce%, the arbitrary code execution and payloads. What inputs does TaskBot make in order to take over the game? There's quite a lot actually. The initial payloads take 1,136 frames of input to inject. It all starts with multiple layers of bootstrapping. As you'll soon see, running controller data as assembly instructions is very slow and limited. The first thing that should be done with the ability to do this is to write a small program in memory that allows this process of injecting data and code into the game via the controllers more efficient. In fact, this is done 3 times, A program is written that will write a program that will write a program that will allow for data to be transferred very quickly, all while still being able to control Link and play the game in the meantime. First, let's talk a bit about treating the controller data as assembly code. As I mentioned at the start of the video, there are just 24 bytes of memory dedicated to the controllers. 2 bytes for the buttons, 2 bytes for the analog stick, 1 error code byte, and 1 0 byte. 4 of these sets, 1 for each controller. A MIPS assembly instruction is always 32 bits long, or 4 bytes, and aligned to a 4-byte boundary. So if the controllers are treated as assembly instructions, here is how they will be organized. The first instruction consists of the first controller's buttons and analog stick bytes. The second instruction is the first controller error code, a 0 byte, and then the second controller buttons. Then the third instruction is the second controller analog bytes, its error code, and then a 0 byte. The next 3 instructions are the same, just for controllers 3 and 4. If a controller is connected, which all 4 are in our case, the error code is just 0, denoting no error. This means these 4 instructions will always be half 0, which is pretty useless. Not to mention that other code in the game zeroes out all of the input from controllers in 2 and 4 already, since those were used for some debugging features, and to disable them from being used, the controller data is zeroed out before any other code can read it. This leaves us with 2 instructions we fully control. Well, almost. There are only 14 buttons on the N64 controller, which means there are 2 bits in this data byte that will always be 0. This means that if we want to encode controller data as assembly instructions, we are limited to instructions that have zeros in these 2 bits. After executing the controller data as code, we still need to return back to normal game function. We can't just let the program counter keep marching down past the controller data, or the game will likely crash. This means we have to reserve our last instruction as a jump back to safety. Remember, we are coming from the function that runs as part of the wonder item code, so we need to return from that function. Interestingly, because of these 2 bits that are forced to be 0, we can't just encode a return instruction directly. Instead, we have to jump to a return instruction that is nearby. Unfortunately, this means we are now limited to a single instruction. Now, as long as the wonder item is on screen, this code will be run on every single frame, and we can change which buttons are being pressed on each frame. So we can execute whatever code we would like, as long as we run it at a lowly frequency of 1 instruction per frame. And remember that Ocarina of Time runs at 20 frames per second. And actually, in order to account for lag frames, where one of our controller inputs may be skipped, the same controller input is held for 2 frames. That way, if there is a frame that lags out and skips one of our inputs, each instruction is still executed at least once. This gives us a final speed of 1 instruction per 2 frames at 20 frames per second, or about 10 instructions per second. It's no wonder why the first thing we want to do is make this process a bit faster. What can we even do with 1 instruction? Not only are our instructions not even contiguous, they are executed on completely different frames, so it may seem like we can't even load or store data to or from anywhere, or else it would just get overwritten. Well, it turns out there is a register in the processor, the global pointer register, that is not used by the game at all. Therefore, with 1 instruction, we can load a 16-bit value into the GP register. Then the next instruction we encode can store that 16-bit value somewhere in memory. This is what our first bootstrapper does. It alternates loads and stores in order to write a program into memory at a rate of about 10 bytes per second. That program is what we will call bootstrapper number 2. After bootstrapper number 1 writes its last byte, it encodes a jump instruction to the beginning of the program it just wrote. Bootstrapper number 2 runs like normal code all at once in a single frame. It patches the code that handles pulling the raw controller data and dumping it into memory, It disables the zeroing out of controllers 2 and 4, and also just jumps straight to the controller data right then and there, instead of having to go through the modified Wonder Item Actor overlay. This is because the Actor overlay is only run at 20 frames per second, whereas this function is run at 60 frames per second, tripling the frequency that code can be run from the controllers. It also undoes the Wonder Item Actor overlay modification we made earlier, since we only need one source of arbitrary code execution after all. With these modifications, we can inject and run code much faster. We are still limited to one instruction per frame, but we are able to execute our code at 60 frames per second instead of 20. Also, the code we modified runs regardless of lag frames, so we don't have to duplicate each instruction anymore. This means we have increased our speed to 2 bytes per 2 frames at 60 frames per second, or about 60 bytes per second. This is still too slow for what we'd like to do, so we have Bootstrapper number 3 write another program, Bootstrapper number 4, to really ramp things up. Once it is done injecting its code, it encodes a jump instruction with the controllers again, just like before, and jumps to the start of the code it just wrote, Bootstrapper number 4. Unlike Bootstrapper number 2, Bootstrapper number 4 is also intended to be run on every frame. When Bootstrapper number 4 is active, the controllers are still being executed as code, but the first controller just jumps to the start of Bootstrapper number 4's code. This leaves us with the other 3 controllers that can encode extra data. Before, we couldn't use these controllers because they were zeroed out, and because they had to encode that extra instruction to jump to safety. However, now they aren't zeroed out, and we can treat them as data instead. Bootstrapper number 4 reads 64 bits of data, 30 bits each from controllers 3 and 4, and 4 bits from controller 2, and writes these to the region of memory dedicated to the expansion pack. This is what will be the final payload and will allow for very fast data injection. At 64 bits per frame at 60 frames per second, we are now able to inject code at a rate of about 480 bytes per second. Finally, Bootstrapper number 4 completes its injection of the final payload, dubbed the Hyperspeed Loader. It patches the controller polling function to call the hyperspeed loader instead of the controller data. Now the controller data is no longer being interpreted as instructions, but as data only. It leaves the first controller inputs alone so that the player can still control Link as normal, but it can also read all of the other 90 bits from the other 3 controllers. Not only that, but the controllers are now pulled 8 times per frame instead of just once. At 90 bits, 8 times per frame, at 60 frames per second, we now have the ability to inject arbitrary code and data at a rate of about 5,400 bytes per second. This brings us to part 3. How is this ability to inject lots of data very quickly used to create all of the custom content shown in the Triforce % run? In other words, what does the hyperspeed loader do with the data it receives? It grabs the 90 bits from the controller data 8 times per frame, which results in 90 bytes of data that forms a single packet. Each packet includes 85 bytes of payload data, a 4-byte cyclic redundancy check, or CRC, and a 1-byte command ID. What the hyperspeed loader does with this data on that frame depends on the command ID. There were 3 main command types used in the Triforce % run. The first of which was a simple data block transfer. Within that 85 bytes allocated to the payload for this packet, up to 81 bytes of data are included, along with a 4-byte pointer that denotes where in memory to write this data. This can be used to upload basically anything to the N64's memory: audio, graphics, models, textures, more code, you name it. The second command type was a function call. This packet included a 4-byte pointer to a function that already exists in memory to invoke. It also includes up to 4 32-bit arguments to this function if necessary. A function with more arguments than this would not be able to be called with this method. And the third command was used for copying the live stream chat messages into the game as they were sent during the run in real time. Multiple messages could fit into a single packet, and they would be stored in a buffer. Then another process took all of the messages currently in the buffer and displayed them onto the screen during the final cutscene of the run. This is really all the hyperspeed loader was capable of, but with years of effort and lots of creativity from a large team of people, an entirely custom storyline complete with gameplay, a plot, and created assets could be injected into the game in real time. The last thing I wanted to touch on was the error checking for the packets. Each packet has a 4-byte CRC, which allows the hyperspeed loader to detect if there happen to be any errors with the data it picked up from the controllers. Also, if the game is in the middle of a loading zone or loading screen, sometimes one or more packets can just be completely skipped. If there was an error, we would need to send the packet again, or else there may be glitches present. But how do we send data in reverse? That is, have TaskBot read data from the game via the controllers. The first idea that may come to mind is using a controller pack, a memory card that can be inserted into each controller. This would work, but it would limit this whole injecting process to a machine such as TaskBot. A human player can press buttons on a controller, maybe not as quickly as we saw here, but they cannot read the contents of a controller pack directly. This philosophy can also be seen from the fact that the 2 extra bits in the controller data are not used at all. Theoretically, these bits do exist, they just aren't mapped to buttons. A machine such as TaskBot could still use these fake buttons, but it was decided that the entire Triforce run could theoretically be done by a human player, or rather a superhuman player who could press the physical buttons on the controllers incredibly fast. So instead, the communication back to the player was accomplished by utilizing the N64 controller rumble pack. Each of controllers 2, 3, and 4 simulated having rumble packs installed in them. Certain combinations of controller rumbling denoted if packets were sent successfully or not, and possibly exactly what kind of error occurred. TaskBot could then monitor the state of the rumbling in the controllers to know if it should try sending a packet again if it needed to. In theory, every packet could be checked for errors directly after being injected, but it turns out that the TaskBot interface via USB has a non-negligible amount of latency, so this would really slow things down. Instead, a bunch of packets were sent in advance at a time, and the number of successful rumbles was counted up. At the end of the bundle, if the number of rumbles was fewer than the number of packets sent, then at least one of them failed, and the entire bundle was sent again. In practice, however, very few failures were ever detected, other than when the player went through loading zones, and the game suspends reading from the controllers altogether. Thank you for watching, and thank you to the Triforce% team for letting me in on the project early in order to share all of this technical information about the run so quickly. Retro Game Mechanics Explained has a Discord server where you can discuss the contents of videos like this one, and also all sorts of programming and game dev topics in general. You can visit discord.rgmechx.com to join, or click the link in the description. If you would like to support the channel, consider becoming a patron at patreon.rgmechx.com. Patrons get ad-free early access to videos and other bonus content.